Then we're going to go over the C++ STL. We're going to look at sets and maps, both ordered and unordered, and kind of take a closer look at the differences between sets and maps implemented using trees versus sets and maps implemented using hashes. And we're going to talk about what the differences are in terms of the data structures, and we're going to see how that's used in the actual STL implementation, what methods are different, what methods are the same but have different complexities, etc. And then hopefully we'll have time to finish up a couple more sections of the textbook, which just covers more collision resolution methods. We got through linear probing. We talked about separate chaining and linear probing last class. Okay? So hopefully we could look at quadratic probing as well as double hashing and rehashing. All right, so just to summarize what we covered last class and what's in the slides. So hash tables are data structures that allow for efficient insert, delete, and lookup. Right? All of one average case, and generally we expect to have that average case, and we'll go a little bit deeper into the math behind that at some point. But for various reasons, there's a lot of work put into designing hash functions in order to ensure that we do practically get that O of 1 insert, delete, and lookup behavior. Okay? So we treat hashes as O of 1 insert, delete, and lookup, despite the fact that the worst case is that every element hashes to the same bucket, and it just ends up being a linked list or a lot of pushing elements off into different buckets if we're using probing, right? So a linked list if we're using separate chaining, or a lot of having to look to the next element if we're using something like linear probing. But in most cases, we could depend on hashing not to fall into that situation. So the way it works is that the main property of hashing is that we don't have access, we have lookup. The difference between access and lookup is access is looking at a position in a data structure. So we could do something like access the 10th element of a vector. With hash maps and hash tables, we do not have access. We never access, right? They're unordered. There is no 10th element. The elements are not ordered. Instead, we have lookup. And lookup means, is the number 30 in the hash table or not? And if it is, we go directly to the spot where it would be. And we know the spot where it would be because to get that spot, we simply apply the hash function to 30, to the value 30, the number we're looking for, and that gives us the index in the hash table where 30 would be if it is in the hash table. If it's not there, it's not in the hash table. Right? For that, the hash function must be a function that maps all of the inputs to a range of 0 to n minus 1, where n is the size of the hash table. Right? A hash table of size n has indices 0 to n minus 1. So the hash function must map every input to 0 to n minus 1. And just to give an example of that, let's look at, let's actually pick up where we left off at the end of last class. I wanted to talk a little bit about the hash function. So a simple hash function for integer inputs is simply mod n, right? If we have a hash table, of size 101, right? Because we prefer hash tables to be to have sizes that are prime numbers for certain mathematical properties. We just take an integer and mod 101. That gives us a result of 0 to 100, which is the range of indices in the hash. But what about non-integer inputs? Well, then the hash function has to be a little more complicated. So here's an example of a simple hash function for strings. One simple way to hash strings is to simply add up all of the ASCII values of the characters. So here we initialize hash value to 0. Then for each character in the key, the key is going to be the value that we're hashing. That's going to be the value in a hash table. The key is going to be the value that we're going to be inserting or deleting. In a hash map, we're going to have a key value pair where the hash function is applied to the key, but the value is often the data we're actually interested in. So the textbook, to simplify its discussions of hashing, just uses hash tables. So the value and the key are the same, right? We just have a key and we're inserting the key into the hash table, or searching for it. So given a string that serves as the key, we're going to go through each character and just add the character to hash val, which is an integer. So when we add a character to an integer, that forces the character's type to be converted to an integer, and when a character is converted to an integer, it's converted to its ASCII value. Okay? So we're just adding up the ASCII values of each character, and then at the end, we're returning that hash val, right, that sum of the ASCII values mod table size. Again, we're going to see mod table size at the end of most hash functions, because once we write some function that maps, a string, an object, whatever, to an integer, we then need to make sure that the value is between 0 and n. And the easiest way to do that is to mod n. Okay, so this is a simple hash function. It's good most of the time, but there are some situations where just adding up ASCII values might not be good enough, right? Especially if you have input that consists of strings that have some specific formatting, right? Like if you have a bunch of strings, that all say my name is blank followed by the name. Depending how many inputs you have, if you have millions of inputs like that, the range of ASCII values is not going to differ all that much compared to the total range of the inputs. So this might not be good all the time. What we ideally want is a hash function that will separate even very similar inputs, that a small change in the input can possibly result in it hashing to a completely different value. In this case, a small change in the input, if you change just one letter, the hash value isn't going to change that much. It's not going to change more than 26, right, if you change one letter, right, of a possible very large table size. Right? What we want is a hash function where even a small change in the input, we change the input, the key value by 1, or we change one letter of the string, it could potentially lead to it hashing to a completely different number in the range. Here's a hash function which is a little bit more complicated, but actually worse. So we might want to do something a little fancier. So let's try something that's going to change the hash value a lot if there's a small change in a character. So here what we're doing is we are exponentiating each successive character. So what we have here is this is going to be a very good hash function for strings of size 3 because any little change in a string of size 3 is going to result in a big change in the hash value, in the result of hashing this, but only within the first 3 letters of the string. So here, we're taking the ASCII value of the first character of the string plus 27 times the ASCII value of the second character. Why 27? What's the significance of 27? Ramsey?
The amount of letters and like an empty.
Good. It's one more than the amount of letters in the alphabet. Plus 729 times the third letter. Okay. So what this is going to do is every sequence of 3 letters is guaranteed to hash to a different position in the hash table, right? A different bucket. Okay. So this second hash function will guarantee that every string with a different first 3 letters hashes to a different position. Does everybody see why that is? So every string with a different first 3 letters hashes to a different position. The big problem for this is, again, if we have some kind of, some strings that have some standard format where the first 3 letters are the same, they're all going to hash to exactly the same value, right? Because this hash function only takes into account the first 3 letters. Okay? So instead, let's take this idea but apply it to all the letters. So here, we're doing the same thing we did for the last one, but applying it to all the letters. And I think here they're using 37 because they're including digits, right? So, if you consider 26 letters plus 10 digits, you get 36 plus 1 is 37. Okay. So, we're using a iterative exponentiation. In other words, for each character, so we start at 0. We start hash val at 0. For each character, we multiply hash val by 27, then add the character. Right? So the first letter in the string, or the first character in the string, is going to get added to hash val. If there's a second character, we're going to multiply that by 37, so we're multiplying the first letter by 37, we're adding the second letter. If there's a third letter, we multiply it by 37 again, which means that the value of that first letter got multiplied by 37 again, so it's now been multiplied by 37 twice. The second letter is multiplied by 37 once, then we add the third letter. If we go on to a fourth letter, we multiply each letter already in by 37 in additional time, right? So what this is going to end up doing is the first letter is going to be multiplied by 37 to the size of the string minus 1. The second letter is going to be multiplied by 37 times to the size of the string minus 2, and so on and so forth. The last letter is going to be just added, right? Not multiplied by 37, right? Second to last is multiplied by 37. Third to last is multiplied by 37 squared, and so on and so forth. And of course, at the end, to ensure that this maps to a range of 0 to n minus 1, we mod by the table size at the end. Okay? So that's an example of a good hash function. Okay? Because a slight change in one letter, especially if that letter is near the beginning, is going to result in a very different value for this hash function. A slight, so who could think of, of one case where this hash function actually might not be so good? So this isn't a perfect hash function, and it does have actually, this still does have one glaring possible weakness. Well, that's just going to hash to 0. And that's not really that much of a problem. So, Ramsey?
I was gonna say you might have a hard time if the string is very big. It might make like a lot of like empty spaces.
Oh, good. So actually, so that's a good observation. So as Ramsey pointed out, it might be a problem if the string is very big. In general, hashing is, as an operation, is expensive. So one big practical downside of hashing, or of using hash tables and hash maps, is the hashing itself. A lookup, once you have the bucket that the value would be in, the lookup's simple. It's just random access. But hashing the value, especially if the data type of the value, if it's a string or if it's an object, the actual hashing of the value can be computationally expensive. Right? So that is something to keep in mind, that even though hashing is O of 1, it's going to be a very expensive O of 1 for several reasons. First of all, you have to compute the hash function, which is going to be more work than than an O of 1 access in a vector, or O of 1 following a link in a linked list. So computing the hash function is going to be expensive, and also if you have to, if you have probing or collisions, any kind of collisions, you may then have to look at, right, so if we're looking for 1, we hash 1 to find it's in bucket 1. The first element of the list is not 1, so we have to keep going through the list, right? If we're using separate chaining. If we're using linear probing, right, same thing, right? If we've just inserted 1889, so if we've just inserted 1889 and 49, we want to look for 49. We look here first, it's not there, we have to look a second place. Hashing is O of 1, lookup, insert, delete, but is it expensive? Computing the hash function itself is a very expensive O of 1 operation. We call it O of 1 because hashing these strings we call it O of 1 because the computation it takes to hash an input does not grow with the size of the hash table. It does not grow with the number of inputs, but it does grow with the length of the input itself. Right? So it's not efficient, but it's not linked to the size of the hash table. It's linked to the actual length of the inputs, which can be problematic in certain cases. It's usually not something we consider when analyzing an algorithm, right? Again, because the length of the input itself is not n, the number of inputs is n, right? So, yeah, while the cost of hashing does not grow with the number of inputs, it can grow with the size of the individual input. So yes, excellent observation. But what I want to point out was that while changing a single character in this string, in the middle of the string or the beginning of the string, will give you a completely different result. If you do have a bunch of strings that all follow a format where, where most of the string is the same and then only the very end of the string is different, we'll notice that changing the last few characters has a limited effect on the value on the output of the hash function. So that could be a slight problem. Ideally, we wouldn't want that situation. Ideally, we would want a hash function where any change anywhere will most likely create a big change in the bucket that we attempt to place the element in, right? We want a small change in the element to just kind of completely randomize where it gets put in the hash, right? So that if we change one letter by one, if we change one D to an E in the string, we want that second string to go somewhere completely different from that first string. So that's what we want out of a hash function. Right? We want a hash function to place elements uniformly among the hash and unpredictably, so that small changes in the element itself will usually result in large changes in terms of what bucket it gets put in. That's going to prevent the kind of clustering we saw in this example. So that's how a hash table works. Again, we have lookup, not access, and for the lookup, we apply a hash function to the element, and the result of the hash function tells us where in the hash table that element will be if it's there. We look there, if it's there, we found it, if it's not there, it's not in the hash table, and then we're done. O of 1. And I'm not going to go over direct address table again, but we went over this last class, and this is just the kind of a simpler version, or the kind of basis upon which hash tables are built. Okay. So if you don't understand this, just review direct address table. So the example of bit set and a vector of just counts of items. And then when we look at the limitations, we see that, well, what we see is direct address tables are extraordinarily efficient, but very limited in use. And in order to apply their efficiency, to use their efficiency more generally, that's what hash functions do, right? Hash functions allow us to use the efficiency of direct address tables while bypassing the limitations practically. Okay, so let's take a look at the C++ STL and a couple of LeetCode problems, and we'll see how sets work. First of all, how sets and maps work, and second of all, how ordered versus unordered sets and maps work.
Direct address tables need like contiguous memory hashes, but
No, hashes do use contiguous memory. Hashes need contiguous memory. The reason is you need random access to the bucket that you're placing the item in. Right? So let's say you have a string, right, and you want to search for the string. So you apply the hash function to the string, right? And the result, and let's say the hash table is size 1,000. The result comes out to 424, right? So you look in position 424 to see if that string is in the hash table or not. For that to be O of 1, you need random access to position 424. Michael?
Using a similar data structure, but the hash function allows you to know where to index.
Yes. So, well, with direct address tables, we basically don't have a hash function. It's just we put the element directly in the index that its value is. So we put, the value of 7 in index 7. We put the value of 8 in index 8, and so on and so forth. The problem with that is that that's only useful for inputs which consist of positive integers within a small range. So let's take a look at unordered sets and maps. And there's one thing in particular I want to look at first. And that is an unordered map, the bracket operator. So maps, both the unordered and ordered map has this bracket operator. Sets do not. Right, so here's unordered set. Okay. No bracket operator. Now, so in sets, you can't, say, well, give me, the 10th element like you can in a vector. Right? Linked lists also don't have the bracket operator. Right? So lists also no bracket operator. Only vectors and maps. But in maps, the bracket operator is not at all the same as in a vector. The bracket operator in a map is going to hash whatever is in the brackets and look in that position. Right? So it hashes whatever's in the brackets first before looking in that position. Right? So if you have a map, right, let's say you have a map called nums, and you write, nums sub 35, right, it doesn't look in the 35th position. It looks in whatever position the value of 35 hashes to. Okay? Which means that you could also put non-integer values in the brackets. So let's say you have, a container of strings, and I guess let's call it words, right? So let's say you have a container of strings called words, right? So you could write something like, words, and then in the brackets, computer, right? And it will look for the word computer in the hash table by applying the hash function to the string computer and looking in that position. Basically like a dictionary in Python, if you've worked with dictionaries in Python. Okay? So, again, the bracket operator for maps works completely differently from the bracket operator for vectors. Well, I guess not completely differently. The big difference is that it applies the hash function to whatever's in the brackets before looking in that position, which gives it a very different functionality. Sets do not have this bracket operator. Now, in unordered maps, so in hash maps, the bracket operator has a few side effects as well that I talk about in the homework assignment. So let's take look at the homework assignment. And so the bracket operator can be used to both access and write to an element with a specified key, which I guess is the same that you could use the bracket operator for a vector. But as a side effect, it automatically creates an element with the key that you look for if it doesn't already exist, which is something you need to be aware of, right? It is definitely potentially useful. It's very useful if you're trying to do something like just insert an element into a set, right? Or, well, a map, I should say. Okay? So if you're just trying to insert an element into a map, usually what you do is you search for it first to see if it's there, and if it's not there, you insert it. In this case, just searching for it does all of that, right? Just using the bracket operator does both things, right? It looks for it, and if it's not there, it automatically creates it with a default value. And that's something you have to be a little bit careful about because that you might not intend. So you could use it if you need to insert X if X is not already in the map. You cannot just use it to check, right? Because again, if you write my map X, it will automatically create an element with the key of X. So you will always get the result that it's already there, because it'll create it. So you could use it to increment a value or alter a value. Okay. So, not just increment, but you might write something like, my map X equals 7, right? So if you write my map of X equals 7, if there's already an element in there with a key of X, then it will overwrite it. If there's not, it will create it and give it the value of 7. Let's look at a couple of other ways to check if elements are in maps and sets, and create elements in maps and sets, and alter elements in maps, right? We don't really alter elements in sets, right? In maps, we could change an element by changing its value, because it's a key value pair. In a set, we don't change an element. If we need to change an element, we just delete it and insert the new element. Okay. But in maps, we could change an element by changing its value, because it's a key value pair. So let's start with finding an element. So in a set, there are a couple of ways to determine if an element is in that set. Now, in C++ 17, there is not a Boolean find method. Right? By that I mean there is no method that just tells you if an element exists in a set or not as a Boolean. In C++ 20 there is, but we're using C++ 17 because that's the compiler on the CS network, and that's the compiler that Gradescope uses. Right? So, just FYI, there is a Boolean method to find if an element is in a set in C++ 20, but not 17. Okay? So how do we find if an element is in the set? There are a couple of ways. First is find, but this doesn't give you a Boolean output. Instead, it gives you an iterator to the element. And if the element is not in the set, it gives you set n. So you would use it like this. So something like this, right? So you declare an iterator got equals mySet.findInput. So you're searching for the string input in mySet. And then if got is mySet.end, it was not found. So .find will return the end of the set if the element you're finding is not in the set. So that's one way. Another way is count, where you count the number of elements in the set, and this, actually, I guess this effectively for a set, not multi-set, would serve as a Boolean find, because count in a set can only be 1 or 0. Okay. Question?
If you did got not equal to mySet.end, that means the whatever we were looking for has been found?
Yes,
Oh.
if the result is not equal to mySet.end, then it has been found, and you have its location. So, going back here, so if it's not equal to the end of the set, then you have an iterator to its location. So again, find will give you an iterator to the location of the object you search for. If the object is not in the set, it gives you an iterator to the end of the set. Count gives you the number of elements in the set with the key you're searching for. So technically this function does return 1 if an element with that value exists in the container, and 0 otherwise. In a multi-set, it can be more than 1. Right? In a multi-set, you could have multiple elements of that set. So you could use either find or count for element lookup. You could also actually use, in a hash, not in a set, but in a hash map, you can use the bracket operator for element lookup as well. The way you would do that is the return value Actually, scratch that. Yeah, no, because it'll automatically create that element, so you couldn't use that for element lookup. All right. So all right, let's take a look at some examples of using sets and maps on LeetCode. And then after that, we'll take a look at hash maps and hash sets versus sets and maps implemented with trees. So first, let's take a quick look at the use of a set. Should be unordered set. Although you could actually use either one. Let's see how it works. Just make sure that works. So, yeah, this isn't going to be long enough to take a good look at the time. But let's look at how to use set in this example. Question?
Is there a way to zoom in on the code?
Oh.
Thank you.
You know what I got? Okay, so let's take a look at the problem here, and we'll look at the code there. So this is a simple one. Given an integer array nums, return true if any value appears at least twice in the array, and return false if every element is distinct. So we just want to keep track of the elements that we've already seen. Okay? This is a classic use for a set. Now, obviously, the naive solution would be just go through every pair of elements and check if any pair of elements is the same. If we check if any pair of elements is the same, what would the complexity on that be? Andy?
N squared.
O of n squared, right? Because every pair of elements is O of n squared. Okay? But instead, we want to use a set. Okay? And mathematically, the idea behind this is very simple. We simply keep a set of every element we've already seen, and for every next element in the vector, we check if that element was already seen. Right? Simple enough. Let's look at the code. So, now, either set will work. An unordered set will be a little bit more efficient. So we keep a set of integers called seen. Then, for each element in the vector, if seen.countx, so if we've seen it more than 0 times, so if we've seen any occurrences of the number already, we return true. Okay. If not, we insert it, right? We don't need an else, because if we found it, we return and we're done. Okay? So if not, we insert it. And we go through every element in the vector, and if we never see a second occurrence of an item and never return true and exit the loop, then we return false. So again, basic use of a set. I'm using dot count to check if the item is already in the set. Questions?
The set obviously makes more sense for this case, but if you use an unordered map, it would be just sufficient, right?
Yeah, well, algorithmically, yes. Practically, you would be using extra memory and like initialize or inserting default values into positions you don't need to. So, you know, like algorithmically, so first let's analyze this algorithmically, right? So using a hash table, what's the complexity of this? O of n, right? It's very simple. You just, you go through the vector, and you just use scene.count, okay? And scene.insert, right? Now, like I said, lookup and insert in a hash are both O of 1. Okay? So each of these is O of 1. So you loop n times with a couple of O of 1 operations. That's O of n. Andy?
Are we inserting the duplicates in the set?
Yes.
Okay.
Yes, the set is scene, right? So it's scene.insert. Okay, so scene is the set name. And to verify that, let's go to the unordered set reference, and let's make sure that find is in fact complexity. So yes, the average case is constant. Worst case is linear container size, but again, I'll talk at some point about why we don't care as much about the worst case of hashing as we do about the worst case of some sorting algorithms or some other data structures. So we're interested in the average case for hash-based data structures. So the average case of find is constant, and we use insert. Let's look at insert. Again, single element insertions, average case is constant. Multiple elements, average case is number of elements inserted, right? So, it's just constant per element. Right, so that's it. Questions about that? Andy?
Why did you use the method .count again?
That's what I use to find if the element is already in the hash table scene.
Oh, okay.
Count returns how many occurrences of X are already in the set, right? Which in a regular set is either 0 or 1.
Okay. So you're looking for the count of X, but then you insert it?
Yes, but we insert it after we
Okay.
see if it's already there.
Okay.
Right? If it's already there, then we know we're seeing a second occurrence of X.
That makes sense.
So we return true. If it's not already there, then we insert it.
Thank you.
All right, good. Any other questions? So let's look at an example now using a map. Okay. So this is toSum. Given an integer nums and an integer target, return indices of the two numbers such that they add up to target. Now, toSum, if you don't need the indices, but only need to say whether there exists two elements that add up to target or not, then you could do that with a set, right? You just put each number in a set, and for each new number, you see if target minus that number is already in the set, right? So if you don't need to return the indices, you don't need to use a map. You could just use the same approach we used here, right? Except instead of scene.count x, it would be scene.count target minus x. So that would be the only change you would need to make for twosome if you didn't need to return the indices. Does that make sense to everyone? Because you just want to see if two numbers add up to target. But it is asking us to return the indices. So how do we track the indices? A map, right? So we have a map, a key value pair, where the key is the number, right? Each number, and the value is the index where it was seen, right? Which I know is kind of like switching things, because I'm essentially saying we're using the value as the key, and for the, right, so we're using the value of the number in the vector as the key for the hash map, and we're using the index of the value in the vector as the value for the hash map. So again, the value of the number in the vector is used as the key for the hash map. The index of that value is used as the value for the hash map. So let me go ahead and put that in here. Make it a little bigger. So we're going to start by declaring an unordered map, okay? Mapping integer to integer. Okay? And in the comments I noted that the key value pair is the value and the index. Okay? Right? Value in index refers to of the number in nums. Okay? So when we declare a map, we have to declare its type as a pair. The first part of the pair is the key, the second part of the pair is the value. Okay, so then I have a vector of answers. Assume that each input would have exactly. I guess because it asks for the answer as a vector of two elements, I guess. Right, yeah. Yeah. So it asks for the answer as a vector. So I declare the answer as a vector. Okay. So now standard traversal, right? Standard traversal of an STL container using an iterator. Again, same standard traversal we used for vector or list is the same way this is the vector we're traversing, right? So, standard traversal of a vector using iterators. We start at nums.begin, we go to nums.end, we increment the iterator each time. So first, I search for target minus the value of the iterator. If I find target minus the value of the iterator, right, if I find that that is already in the set, that means that I have just found the second element that adds up to target. So if target minus the value of the iterator is already in the set, I have just found my answer. In that case, I'm going to push back it minus nums.begin, right? What does it minus nums dot begin give me?
The index.
The index, right? That's how you get index from an iterator, right? It minus nums dot begin. And I also push back scene target minus what it points to. Now, let's look at this syntax a little bit. So, I'm pushing onto my answer, scene target minus the value of it. So this is using the lookup capability of an unordered map. Remember, like I said, in an unordered map, the bracket operator works differently from in a vector, right? This is not the position of target, which is here, right? Minus what it points to, right? So target minus the value of it is that second number that adds up to x, right? We're looking for two numbers that add up to x, right? Star it is the first number, target minus star it is that second number. Right? So we're not going to that index, but instead we're applying a hash function to that. And when we apply a hash function to that second value, right, or any value, when we apply a hash function to that, that's going to return the value associated with the key. And in this case, that value associated with the key is going to be the index, which we're going to see in the next line. So to understand this, we want to take a look at how we're inserting the elements. So now, if the number we just saw, on the other hand, does not add to something, does not add up with something we've already seen to target, then we're going to insert it into the map. And here's how we're going to insert it into the map. So when we insert something into a map, we insert a key value pair. Now actually that's not the only thing we can insert into a map. We could just insert a key, in which case the value is the default, but here we want to insert a key value pair. So this is a pair in the curly brackets where the key is star it and the value is it minus nums dot begin, which is the index of it. So again, we're inserting the value, meaning the number in the vector, and then its position in the vector. Right? So the value of the number in the vector is the key, and its position is the value. So when we return this as our second answer, when we push this back onto our second answer, what does scene sub target minus it give us? It gives us this it minus nums dot begin. Because again, the way that we access a map is the bracket returns not the key value pair, but just the value. Because we don't need the key, we know the key, because we just put the key right into the brackets. If we want the key, we just have what we put in the brackets, right? So we already know the key, because the key goes in the brackets. Well, what it returns is just the value. No? Yes. Yes. So of the key value pair, it returns the value. So let me just go to an example of that. So here's an example using strings where we're mapping a string to a string, which shows us a little bit more of a difference between maps and vectors, because we couldn't do anything with this, like, this is not allowed for vectors. So here we're inserting a key value pair where the key is bakery and the value is Barbara. So this is just a listing of different departments and who works in each department. So then we can read, so standard string name equals my map bakery. So my map bakery would just return the associated value, which is Barbara. So this would just return the associated value. We don't need to return the key. We already know what the key is because we just put that in the brackets. So this just returns the value, which is it minus nums.begin for the value, for the number that adds up with the other number to give us target. All right. Questions? So, both of these answers would work with either ordered or unordered sets or maps. The difference being that insert, delete, and lookup would be O of 1 average case with an unordered set or map, and O of n log n average case with an ordered set or map, which is tree-based. And I don't know if it's going to show on these examples. I would have to look at the, 10 to the 5th. That's only 10,000. Yeah, no, the inputs here are small enough that I think even if we use ordered versus unordered, we're just going to get 0 milliseconds all the time. Let's see, with an unordered map, oh, 4 milliseconds. Okay, that's interesting. Let's see what happens if I change it to a regular map. So notice that it runs just fine, 7 milliseconds, right? So a little bit slower with an ordered map, right? With a regular map versus unordered. Okay? So we can see the difference in terms of runtime. All right, questions? So, the last topic I want to cover today is the difference between unordered and ordered sets and maps. So let's look at set versus unordered set. And we'll notice it's going to be mostly the same. Well, actually not really. So we just saw that we could use it the same way in code. That in the code, if you just replace unordered set with set, it works just fine. And likewise, if we change unordered map to map, it works just fine. So we'll notice that here's unordered set. We only have begin and end iterators. For an ordered set, we also have reverse iterators and constant iterators. Because for an unordered set, we only have forward iterators. Remember that random access iterators are the most powerful iterators, and they have the most functionality, followed by bidirectional, then forward. Right? So, because we have forward iterators rather than bidirectional iterators, we're missing a few of the iterator methods in unordered set. In unordered set, we have element lookup. In an ordered set, find and count are listed under operations instead of lookup. So, ordered set, find and count are listed under operations. Unordered set, they're listed under lookup. Equal range is also there. Ordered set also has lower and upper bound. So first of all, why are find and count, which do the exact same thing, by the way, listed under operations in a tree-based set, but lookup in a hash-based set? Anybody want to speculate on that? Why does that make sense?
Does that mean to do with the complexity?
Good, right? So it does have to do with the complexity. Yes, right? So what's involved in find in a tree? Michael? Right? Well, not really a traversal. Like traversal usually implies going through the whole thing, right? But a search, right? So it's a search, right? So it's a binary search. So find or count in a tree-based data structure requires searching the tree, right? So a binary search. Binary search is not a lookup, right? It's an operation. Whereas in a hash table, you simply